So I'm playing with this. This is an audio heterodyne. This circuit is basically like an heterodyne of a radio. It has a local oscillator and it picks an high frequency, in this case an ultrasound, picked by this ultrasound capsule here. And mixing the frequency of the local oscillator and the ultrasound, it makes the difference of the two frequencies, and this difference is amplified by an audio amplifier and played by this speaker. Okay, we have here this needle that I will let it fall on a tile here, and it will make this small sound that you can barely hear. It's an high-pitched sound. But let's see with our device. Now it's turned on, and it makes this low sound that is quite different. But this is not just the same sound of before and amplified and maybe varied in frequency response. It's an ultrasound that was inaudible before, and now instead it's audible. I found this schematic online. There are a pair of versions. This is the version with the CD4066 chip and a pair of operational amplifiers and a small audio amplifier. And there's also the version with the SA602, that is a special chip used for mixers or heterodynes, but I don't want to use that. This is simpler. Anyways, the source of this circuit is unknown, actually, the original source. You only find the schematic in mirror sites, and I refuse categorically to link mirror sites. Anyways, I also tried, instead of this ultrasound capsule, to use a piezo capsule, a piezo speaker, a small piezo speaker, but the best results are with this ultrasound capsule. The problem is that this capsule resonates at 40 kilohertz. That is an ultrasound, but it's too specific, it's not broad, so it's most sensitive at 40 kilohertz. Anyways, this circuit is also called butt detector, because apparently butts that they have their audio radar, their ultrasound radar that they use to spatially locate and find objects, and apart their typical that they make, they also make ultrasounds that apparently you can hear with a device like this. So let's do other tests. Here I have two coins that are identical. These are 20 euro cents. They are identical except for the back drawing that makes them slightly different. Anyways, these coins sound the same on the tile, but with the ultrasound heterodyne they sound different. This is higher. Let's swap the place. Higher again. Lower again. Let's swap the place. This is lower and this is higher. They are the same coin. No modifications. This is higher, lower, higher, lower. Cool, huh? And this because the two coins make an ultrasound that is slightly different in frequency. And when you lower the frequency in a subtractive way, you end up with two audible sounds that have a much bigger proportionally frequency difference, and they will sound totally different. Anyways, this is the potentiometer that adjusts the frequency of the local oscillator, and the higher the frequency is of the local oscillator, the biggest will be the difference of the subtraction. The lower will be the frequency of the local oscillator, the lowest will be the subtraction of the frequency. Other two tests are these. Let's turn it on. Okay, if I put my fingers in front of the capsule and do this, it makes this sound that I'm not sure if it's actually ultrasound, but it probably is. Anyways, one of the coolest tests are with keys. I have this bunch of keys here that are my keys, and if I jiggle them, it makes this silly sound. I'm in front of the capsule, and if I go away and go quite far, we are at like 3 meters of distance, it still makes the sound, and it's quite loud. It's very loud. And I tested it at like 10 meters and it still makes the sound. Still loud. So, I'm trying to make a modest power TV broadcasting station. This is my setup at the moment. I have an HDMI to composite video converter that comes from my PC. Here I have this modulator here, a frequency modulator, UHF modulator, that is a kit from a magazine of decades ago. Anyways, this makes a modest power in the order of, I don't know, 1 milliwatt or maybe even less, and it's intended for being connected to the antenna input of a TV. Then there's this Chinese antenna amplifier for TVs or cable TVs, and I also made cascaded after this a DIY amplifier with a power transistor, a small power transistor, for making the 518 megahertz of signal. And then there's this ground plane antenna that is quite easy to make. Anyways, now the thing is already broadcasting on this small TV, CRT TV, black and white, and the amplifier is off. The power amplifier is off. I have this field strength meter. Let's turn it on. And it's already, if I put it on the antenna, it's already making a signal, but it's this one that is making the power. We have here like, I don't know, 5 milliwatts, and this can cover just some meters. Anyways, let's power on the final amplifier. Okay, now it's on. Now it picks better, and it's already much more powerful, as you can see. But the problem is this high sensitivity plus lower sensitivity, and as you can see, I don't know, this can be in the order of 20 milliwatts, 50 milliwatts. The problem is that I can't cover my whole house going around with this TV, because this thing seems to be not much powerful. The heatsink that I made on the transistor heats up a bit, but maybe it's just the bias of the base current that makes it hot. Anyways, this is the best setup that I could make. Okay, let's turn off the power amplifier, okay, because it heats up. Anyways, you see this tin foil Why? Because this thing, for the high gain that it has, it self-oscillates. And an easy solution, apart these ferrites that made little effect, was to make a ground plane and grounding with a sheet of tinfoil, all the RF parts, including the amplifier, the final amplifier. And I don't know, maybe the antenna is too close to the other amplifiers. Maybe it makes sometimes a self-oscillation. I have this other amplifier here, but I can't put it in the middle because it self-oscillates. Anyways, the tinfoil works for avoiding self-oscillations, but I can't exceed in amplification, in gain, because anyways modulators are known to be very, very low in power because they have to be hooked up directly on the antenna input of TVs. Anyways, this semi-failed project because the range is quite low, but yeah, I like it anyways. Whatever. This is instead a modulator, just a modulator, not a transmitter. In fact, it's connected through the antenna cable to this TV, black and white TV, Italian TV. Let's turn it on. Here. Let's turn on the TV. Here. And let's wait. Whoa! Amazing. Okay, this is nice at the end. It's quite clear, and the signal comes from my PC. Again, this converter here from HDMI to composite. And this modulator is crystal controlled. You can see the crystal here at 27 MHz, and so the frequency is quite stable. Anyways, I found the schematic online on a nice guide that I link in the description of the video below. And the particular of this modulator here is that it makes harmonics frequencies each every time every 27 megahertz. The crystal is 27 megahertz. So you start picking this thing at like at 54 megahertz. We are at 54 megahertz here now, VHF. I wanted a VHF modulator because I just had UHF modulators, and I generally don't like a frequency so high, so I needed something with a lower frequency. Anyways, you pick it up to UHF every 27 megahertz. This can't be amplified probably, but it's still nice. And another thing, it doesn't have audio, but it works pretty well. We are now black and white, but it also works with color, almost certainly. So I wanted to perfection this circuit here. This is an electronic transformer. An electronic transformer is a device that was used some time ago to power 12 volts halogen light bulbs at sometimes hundreds of watts also. Anyways, in this case I'm using this circuit, this schematic, let's call it, for driving a DC flyback and making arcs. And I perfectioned it to modifying the feedback system. And there are no electrolytic capacitors in all the circuit. In fact, this thing runs at pulsed DC out of mains, and the arcs are noisy. Anyways, it uses BJTs, not MOSFETs, and to limit the current on the output also, I'm using ballasts here. This is my ballast board, and I'm using just these two ballasts here put in parallel that are in series with mains here in the circuit. So the original circuit of electronic transformers uses a small transformer in series with the primary of the load transformer. In this case, instead, I'm using a separate transformer here that is powered directly by the half bridge of the driver. This is a driver after all. And this small transformer is basically just a common mode choke out of a TV that has a bunch of turns for the primary and just 5 plus 5 turns for driving the bases of the BJTs. This is the improvement that I made. Anyways, this thing makes arcs of like 4 centimeters long of voltage, so it's like 40 kilovolts or kind. Anyways, I'm using a DC flyback, a regular DC flyback, medium size, and it has 25 turns of enameled wire as primary, and it's ungapped. I opened the core and took away the gap to make a forward transformer. Okay, let's try this thing. Now we have a bit more of ballast. There's just this 18 watts ballast more because the voltage is a bit lower. And we have directly the 230 volts or almost without the variac. A bit more of 4 centimeters of jumping distance. And let's try. Let's turn it on. Okay. It's both hot and at high voltage. And you can hear the noise that is pulsed DC at 100 Hz. There's a full bridge here. Okay. Safety measure. Okay. Anyways, the BJTs get warm. Maybe one a bit more of the other, this one here, because the load is rectified. It's there are diodes. Anyways, this is it. So I'm again at a VTTC, but this time with a new approach. You maybe have seen that I used a relay here for driving the primary of the MOT for making a staccato controller for the VTTC. But this time, instead of driving the primary at mains voltage, I wanted to try a relay under oil, as you can see, for switching literally the high voltage out of the MOT. And here is what I made. And you see two relays, not one, because this one is for the high voltage out of the MOT, for the anode supply of the VTTC, and this other one instead is for the grid 2 of a pentode, because I needed two relays, because I have two supplies usually. Anyways, you see also these components here. These are a snubber that I put just in case for a safety measure, and it's made with high voltage capacitors and resistors of some hundreds of volts. Anyways, I'm using not a doubler on the MOT, but just a diode, so the maximum voltage that the relay must withstand is like 3 kilovolts. And the duration is also shorter, and the relay also switches on and off just during the peak voltage of the negative half wave, and considering there's a diode, there will be basically no current. Anyways, the controller of these relays here is this one that maybe you have already seen. Anyways, this circuit is in sync with mains through this cable, and it makes a pulse of 1 hertz, just 1/2 wave, or it's configurable for making 2 pulses, 3 pulses, up to 5 pulses, but generally one pulse. Anyways, I'm not using this relay here because this is for mains voltage, and this controller is also finally adjusted to be in sync with mains through the streamer here, and you have to use a scope for syncing it properly. And the oil slowed down the release, and to make them a bit faster, especially for turning off, for releasing, I put a resistor in series with the freewheeling diode of the relay, and this resistor allows an higher voltage peak on the coil of the relay when opening. But considering this, the voltage was so high that initially it popped my MOSFET, the MOSFET that drives the release, so I had to use a chunkier MOSFET here. This is 200 volts instead of a 27000. Okay, let's try this thing. The tube is hot, the cathode is hot. Let's turn on the staccato controller and let's see the LED flashing. Okay, and let's see if we can see the release moving. There's a camera sync effect, sadly, because the 25 Hz of the camera is in sync with mains, with the 50 Hz of mains. Sadly. Anyways, let's turn off this light here. Let's turn on the variac. And let's crank the variac. The camera sync effect is also on the sparks, and sometimes it cuts the length of the spark on the video. I'm not making excuses. It actually shows a spark that is shorter, but it's longer in reality. Okay, let's increase the power. Okay. Okay, this is basically the maximum. I don't want to go past. You can hear the moth humming. Yeah, and it works. We are at 100% of variac. This is 100%. Okay, let's turn it down. And okay. So, thanks for having watched my video, and bye.